For today's class, what we're going to look at are measures of central tendency. And this is the first week where we're actually going to have to do some math and calculate statistics. So thus far in the semester, we've talked about the concepts behind statistics, the idea of the scientific method. Now we're actually going to do some math, but again, math that you've learned 10 years ago. So nothing new here, just a refresher on some concepts that you should already know. The first type of statistic that we're going to talk about is known as a measure of central tendency. And this description kind of comes from the idea of a distribution of variables. So what is the most frequent, in thinking of that idea of central tendency, what are you typically probably going to see? So a measure of central tendency, by definition, is a statistic that identifies the center of a distribution. And we have been talking about distributions in terms of a normal curve. So the measure of central tendency is going to be our line in the middle. Now, in a symmetric, unimodal distribution, a standardized normal distribution, we get a nice bell-shaped curve with one peak, and it's symmetrical on both sides. So if we folded it over, it would be on top of itself. That's what I attempt to draw whenever I do these normal curves. So the central tendency is a single score, or let's think of this as a value. That's the most typical, common, frequently occurring, the one you're most likely to get. So if we were all here in person today, one of the things that I would use as a measure of central tendency is when we roll dice. Now, when we roll dice, a pair of dice, the most common outcome is 7. It's the outcome that is the sum of 1 and 6, 2 and 5, 3 and 4, and then the reverse side, 4 and 3, 5 and 2, and 6 and 1. So that's the pair that is most likely to happen because it's the pair that contains the probabilities of each of the numbers. So what is the most likely outcome is the one with the highest probability of happening. So I had a whole thing where we'd roll some dice and everybody would roll a pair of dice. I got a whole bag of them in my office. You roll the dice, and then we write them on the board, and then we find what the average is of everybody rolling the dice. Because what we're doing is we're creating a distribution. We're creating a distribution from 2, which is the lowest sum you can get of a pair of dice, snake eyes, 1 and 1, or 12, which is a pair of 6s, boxcars. Right? You roll 2 6s, that's a 12. You cannot roll a pair of dice, and get anything lower than a 2. So there's no zeros, there's no 1s. Conversely, there's nothing higher than 12. So 2 is the minimum, and 12 is the maximum. And if we do this in repeated trials over and over and over and over again, what we should get is a distribution that looks a lot like a normal distribution. So if you want to, you're at home and you find a pair of dice, roll dice for like half an hour. Just go ahead and do it. Keep rolling your dice. And what you should get is you should get a nice even distribution of the probability of everything from 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And as you get closer to 7, you should get these numbers more frequently. So it's going to be a bit chunkier, right? So 7 is going to be our tallest. This is what it'll look like. If we do a bar chart. So So when we say central tendency, the one word that usually comes to mind is average. In some places, average is like an insult. Oh, well, that's fine, you know, we're at the average. Everybody wants to be above average. In the text, we don't really use this term average. What we're going to use a lot is the term mean. The mean value of x is the average value of x. But there are other measures of central tendency, and we'll talk about those, the mode and the median, and talk about the differences between those three and why you might use one versus another. So let's start with the easiest. The easiest is called the mode. The mode is the most common or frequently occurring score. So it's whenever I think of mode, I think of most. Right? Most common, most frequent, most likely, perhaps, if we're talking about probability. And the way to find the mode is to look at a distribution table and find the value with the greatest frequency, the one that happened the most often. So if we're using this sort of figure here, what's the mode? Well, the mode is the one with the highest peak. That's the highest point. But let's think about this for a second. What if I had 2 peaks? Well, then I could have 2 modes. If they're the same number, same occurrence. Let's say you're really good at rolling dice. Really, really good at it. Well, take one dice, a die, and roll that one die over and over and over again. If it's a true die, which means that the weight is distributed equally on each side, if we're in Vegas, what's going to happen? Well, if it's a true die, we should have an equal probability of every outcome. So you should receive the same number of 1s, the same number of 2s, the same number of 3s, 4s, 5s, and 6s. Could. That's a possibility. So then you could have 6 modes out of 6 outcomes. But because life is stochastic and there's always a little bit of randomness to it, you won't have exactly equal numbers. The median. The median is one where we might possibly do some math. The median, like a road median, is placed in the middle. So what value is in the middle of our distribution? Such that we will have equal numbers on both sides of the distribution. The procedure for finding the median involves sorting your data. So putting the data in an order from lowest value to highest value. Now this should give you a little bit of a hint on when you would use the median. Would you use the median when your values of data don't have any sense to the numbers? So when we were talking about assigning a value to religion last week, when we were talking about how to create a nominal level data, the idea of saying, well, Catholicism is 3 because of the Holy Trinity, and Buddhism is 99. Does that mean all the Catholics go before all the Buddhists because their number is lower? So the median is not going to necessarily work for nominal level data unless that number attached to it has some meaning. So step 1, sort your scores from lowest to highest. If I give you 5 numbers, you want to put them in order, from lowest to highest. And then to determine which of those 5 scores are the median, it depends upon how many numbers are actually in your data set. So when you have a data set with 5 values, 5 is an odd number. The way to find which score it is, or which data point it is, you take n equals the number of observations. I have 5 plus 1 and divide by 2. Five plus 1 is 6. 6 divided by 2 is 3. So the third observation is the median. So going back to our data set, 1, 2, 3. So the median value is 13. So that's if it's odd. Now, here's the thing about this. We just came up with a mathematical formula to find the middle. And when I only have 5 values, it's pretty easy to find the middle, because there's 2 on this side and 2 on this side, and that leaves this 1 here in the middle. But let's say your homework gives you 17 or 18 to find. Well, then at that point, it might just be easiest just to put them all in order, use the equation, and go that way. Let's add another number, 27. So now I have 6. I have 6 observations. With 6 observations, I'm going to have the n divided by 2, so 6 divided by 2, that's the third score, plus 3 plus 1, the fourth score, and I'm going to have to take those 2 scores, add them together, and then divide by 2 to find out what the median value should be. So the third observation is 13. The fourth score is 15. 28 divided by 2 is 14. So the median value is 14. Pretty light math here, right? Again, put the bucket on the floor. Let's take a look at what we have to do. We have addition. Right? We have addition and we have division. That's it. Addition and division. The mean, or average, as we've been taught it, the mean involves just a little bit more work. The average value of the variable, this is computed and represented by x bar. Now, x bar. X is just our variable. We use x as a catch-all term. We use x's and y's, and sometimes we use t for time. X is just our variable of interest. The bar is what tells us that it's the mean of x. So we're kind of creating a new constant here, x bar. All right, x bar is equal to, now we got a sigma. This is actually a summation sign. So what we're going to do is we're going to take our data set and we're going to add all of the values of x together. The sum of x. So let's go back to the previous slide. I had a data set that was 8, 12, 13, 15, and 20. Let's just start with those 5 numbers. Make it easiest on ourselves. So what I need to do is I need to add together 8 plus 12 plus 13 plus 15 plus 20. All right, add all of these together. 8 plus 12 is 20. 20 plus 13 is 33. Sorry, 20 plus 13 is 33. 33 plus 15 is 48. And 48 plus 20 is 60. So I've got a calculator here, and so as not to look like an idiot, I will add these together. And that inclination was correct, because that should have been 68, not 60. 48 plus 20 is 68. All right, so 68. That's my sum of all of the x's. Imagine this is little x1, this is x2, x3, x4, x5. Taking the sum of all of those x's and added them together. And now I need to divide by n. And n is the number of observations. I have 5 observations. So 68 divided by 5 is 13.6. So 2 steps. First step, doing the sum of x, taking each observation and adding it together. The second step is to take that sum and then dividing it by the number of observations. So x bar equals sum of x divided by n. Now you'll notice that if we go back to that previous example, that the mean is not the highest peak. And there's a reason for that. In this example, we had a distribution that is positively skewed. So the mean, the median, and the mode are not going to all line up. There's going to be a gap between them. The book really wants you to be able to do this quickly using a frequency distribution table. And so I just want to take a minute to remind you of what those are and what they look like. A frequency distribution table gives us the number of times each individual value of x occurs. That's the f of x. F stands for frequency. So in a frequency distribution table, it'll tell us how many times each of our values occur. Now, I'm going to take a moment here. Let's stay right here for a second. And refer back to this website that I'm trying to get students to use. It's the Survey Documentation and Analysis website, SDA, out of UC Berkeley. This is where you can get these large omnibus national surveys that you can use the data for your course paper. So there's a variable in here called EDUC, E-D-U-C, and it was asking each individual person how many years of schooling, how many grades, actually I'll take back, what's the highest grade that you finished and got credit for. So this is a frequency distribution table. Right here at n, that's the number of times each value appears. So in this data set, 161 people said they never completed a grade. They never went to school and completed a grade. 1,367 people said they completed 20th grade. And I know some of you are thinking, wait a minute, 20th grade? Well, let's think about it. They completed 12th grade, got their high school diploma, and then they did another 4 years of school and got a college degree, and then they went to graduate school. Or maybe some of them are on the 6-year plan, and they did 12 years to graduate, and then they did 6 years to get their undergraduate degree, and then they did 2 more years to get a master's degree. If we look at how many people took this survey, 62,466. That would take a very, very long time to add those together, those 64,000 numbers together one at a time. So taking your data and reducing it down to a frequency distribution table will save you a lot of time. And it'll also make it possible to look at your data. So how would we actually do this? Well, 161 times 0 years would be 0. Plus the 45 that completed 1 grade, plus 45, plus 148 times 2, because they completed 2 grades. And so you'd go on like that. Let me copy this so that we can actually go down and do it. So it would look like 161 times 0 is 0, 45 times 1 is 45, 148 times 2, according to my calculator, is 296, and we would keep on doing this all the way down to 1367 times 20, which is 27,340. So this is our f, this is our x, this is our fx. And then we would add all of these together all the way down through to get us the sum of fx. Here's one that they did. Okay. Here's a frequency distribution table. They want to make a point here. One of the points that they want to make is that the mean as a measure of central tendency is unique because it provides us with a balancing point or a tipping point. Actually, tipping point's a bad word. A balancing point where this is the value where half of the sum of x is under it and half is above it. So here they have a set of scores, 9 scores. So this is the x. They have calculated the mean to be 3. And if you take the difference between x and x bar, so the difference between your value of x and the difference between the mean, when you add and sum all of those together, it equals 0. And if we look at the negative differences, 1 plus 2 plus 2, that's a negative 5. If we add together the positives, 1 plus 1 plus 3, negative 5 plus 5 equals 0. So the sum of the differences between your x and x bars should equal 0. Why do I tell you this? Well, actually, when I'm doing math with Abby, I use this rule as a way to check and make sure that we've computed the mean correctly. Again, second grade math looks kind of simple like this, but it's a way that once you understand how, again, bucket on the floor, how you can take something complicated and simplify it, and you can learn a rule, and we can learn about what the mean actually is, other than just how to compute it. This will help us understand what the mean is in the future when we talk about it, so we can talk about it in an intelligent manner. Now, I've been using X bar because X bar represents the mean of a sample of data. But in statistics, we've talked about this difference before between a sample and the population. What we're doing is we're collecting a sample of data from a larger population, and we want to know the relationship between the sample we collect versus what exists out there in the population. So here's an example that we'll use throughout the semester. Imagine you're Nike and you're making shoes, and you want to sell shoes in the most efficient way possible. You want to make just enough shoes that sell, so that way you don't have leftover inventory. But you recognize that your customers all have different sized feet. So if you're Nike, what do you do? Well, one of the things that Nike should do is Nike should go out and find out how foot size is distributed throughout the population. And they should find out what the average, typical, mean foot size is. Well, they're going to use that sample that they generate, X bar, to represent how they think the population of all the Nike buying people in the world, what shape that distribution takes. When we talk about population parameters, we tend to use Greek letters. So this is mu. It's an M, mu. And that represents our population parameter. Let's think about what we have here. What do we have across these three different measures of central tendency, the mean, the median, and the mode? Well, each of them have their benefits and detractions. The mode is good because it's simple. It's easy to determine, right? Which one occurs most frequently? It's the highest peak, or the largest frequency, or N. So if we go back and we look at our data from the question of which grade have you completed the most, we look here down at the side, this bar here is the tallest. You got to turn your head, or turn your screen, right? This is the highest peak here. It also has the largest percentage, and it's the largest number, 12. So the modal outcome, the most frequent outcome for number of grades completed, is 12. This isn't nominal data, though. This is data from the number of years. That's a count variable. That's more of a continuous thing. The guess could keep going and going and going in school years. But let's think of nominal data, like names. When you get married and have kids, one of the things that you'll consider is, what are you going to name your kid? Well, do you want the name to be popular so that you can go and purchase things with your kid's name on it, like that rack of keychains or license plates? Or do you want your kid to have a name that people know how to spell, Or do you want something completely unique that nobody else has that name that you know of? Well, actually, the Social Security Administration releases yearly data on the popularity of names. So, if you or a friend are having a kid and you have this conversation about names, you can see how popular the name Zachary is, or the name Macy, or the name Abigail, or Jonathan. And so one of the things that my wife and I had a conversation about was we wanted to use a traditional name, but we didn't want it to be the most popular name. And when Abigail was born, we considered naming her Emma. But there were a million Emmas out there. So this data is out there and available. And it gives you a ranking, and you get the order, right? And it's for nominal name data. Compared to the median or the average, the mode is the one that is guaranteed to represent an actual value of the data. For the median, when you have an even number of observations, what you're doing sometimes is calculating the average between those two in the middle. Remember how we had a 13 and a 15, and the average of those two numbers was 14. Well, 14 wasn't represented in our data. Remember this example? Right? The median was 14, but there are no 14s. And when we did the mean of the data again, we got 13.6. Well, what is a 0.6? Maybe that doesn't work for your data. If we're talking about number of children in a family. Right? How many grandkids does a person have? Well, one person has 8, one person has 15. The average is 13.6. Does 13.6 grandkids make sense? Can you have 0.6 of a kid? So the mode, because it relies upon the data that is actually observed, and you're just counting the most frequent, that value is guaranteed to be in your data set. The mode also allows for the possibility of multiple modes. So it allows for the possibility that there are two most popular outcomes. You'll notice that with the mean and the median, you're calculating it down to a single outcome. So let's think of a distribution that is what we would call bimodal. Where is the mean and the median going to show up? The mean and the median are going to be in the middle. Because with the mean, we know that half of the value will be to the left and half of the values will be to the right. And with the median, we know that 50% of the observations will be on one side and 50% of the observations will be on the other side. So imagine if we had two symmetrical bimodal humps in our distribution. And lastly, the mode itself is not affected by outliers. So if we have a situation where you have a distribution with a very long tail, right, this positive skew is going to pull the mean and the median away from the mode. So the fact that Shaq's 23 size shoes exist, if Shaq is part of the sample, that's going to mess up Nike's survey, or people with freakishly large feet. Now, basketball players might purchase a lot of sneakers, but they tend to be the taller people. And to make sure they stay upright, taller people tend to have longer, wider feet. So if you're looking at consumption data with basketball players who are taller buying more sneakers, Nike might want to consider that when they're creating their models of how many shoes to make of each size. And also, since shorter people are less likely to play basketball because, well, they're short and the tall people keep knocking down their shots, they might be less likely to purchase basketball sneakers. They might do something else instead, like play tennis or run. Here's the problems with the mode, though. The mode is just based on one single score, right? The most frequent one. Yes, there can be ties, but still. We have data that has 64,000 observations. And which one are we going to pick? The one that's in the 50th percentile. One of those 64,000 observations. Are we really going to use one observation to represent an entire data set of 64,000 people? And lastly, when we get to the science part of this class, where we're doing hypothesis testing, we can't use the mode. Because the mode gives us nothing about the distribution. Again, it's only about one value of the distribution. So when do you use the mode? Well, names. That's about it. Nominal data. The median. Well, here's the thing about the median. The usefulness of the median depends upon the shape of the distribution. So the median is better as a measure of central tendency when our distribution itself is skewed or asymmetrical. So when we have those outliers that go off the distribution. The median might be better because it takes into account the number of observations, but not the total spread of the observations. However, like the mode, one of its weaknesses is that it only relies on one, if it's an odd number of observations, or two observations, if it's an even number of the total. And it doesn't rely upon the entire distribution of the scores. As a result, because it doesn't represent the entire distribution, we don't use it in hypothesis testing. Which is kind of the whole point of learning statistics. Not just to summarize data, but to actually test a social science hypothesis and try to see how well our sample reflects what's going on in society. And finally, the median doesn't describe bimodal distributions. So again, the situation where we have two humps and we have a median in the middle, we could have two humps, we could have one hump. We don't know the difference. So the mean is the one that we're probably going to go with. The mean is great because it's calculated from all of the scores, right? That's sum of x. Every single score in the distribution is going to contribute equally towards the calculation of the mean. So Shaq's foot is going to be incorporated in there. As a result, because it includes all of the data, we can use it in hypothesis testing, which is what we're here for. A couple of downsides of the mean. One, it's affected by outliers. So the fact that we're using Shaq's data, that's going to move the mean closer to these outliers. So if you have a skewed distribution, you just have to recognize that that's what your mean is doing. And if the shape of the distribution is important to you, using the mean is not going to capture that. It's not going to capture the fact that you might have a bimodal distribution. How would that work? Well, let's think about this for a second. Is there a situation in which we can take a group of people and divide them up and expect different results? Now, this might just be a function of how we size things, but couldn't you imagine a scenario where you have a distribution where one of the humps, one of the curves, is like female shoe size, and then the other hump is male shoe size? Now, I'm pretty sure the sizing rules are different for male and female clothes. I haven't shopped for a lot of female flip-flops or female brown shoes before, but I can imagine that the actual measuring is different. And if we just calculate a mean and assume that the data is for each person in our sample, we might miss out on the fact that what we need to calculate instead is a mean for female and a mean for male. We might need to separate these two out. So actually thinking about the shape of your data and plotting it out and trying to recognize, okay, let's take a look at this. Ideally, if we have a perfectly normal distribution, the mean, the median, and the mode should all be the same. They should all be the same value. And in this case, what we have is a standard normal distribution. The mean, the median, the mode all represent the same value. With skewed distributions, the mean, the median, and the mode won't be the same. And in fact, the pattern of it will tell you which direction the skew is. If the mean is greater than the median and the mode, you have a positively skewed distribution. If the mean, the median, and the mode are greater, if the mean is less than the median and the mode, you have a negatively skewed distribution. If you have a situation where you have multiple modes, well, then what you have is a bimodal distribution. Again, situations where you have two distinct groups in your data that need to be recognized as distinct groups, whether it's the gap between men and women or the difference between, let's say, high school people who went to high school and those that went to college, or something like that. Right? You have a distribution that actually has another reason why they're different. So here's a couple of things to remember. Measures of central tendency like the mean, the median, the mode are best to help us understand the modality, right? The most frequent, the most typical, the average of our distribution. That's what we're trying to do. We're trying to just succinctly describe the value of a variable using one value. What's the typical outcome? A benefit of this is it also gives us the idea of the shape of the distribution and how that distribution could be skewed, or whether it's bimodal, right, or how many humps there are. Reminds me of that children's song, Alice has 2 humps, and then she counts down, Alice has 1 hump, and then the last thing is Alice has no humps, because Alice is a horse. Da-da-da, dad joke, okay? If your distribution turns out to be symmetrical, you're going to want to, or excuse me, asymmetrical, which means that one of the directions pulls on the mean. You're also going to want to consider reporting the median. What we're going to talk about next is the variability of a distribution. How much do the values of our variable differ? But that's for next week. So what you should do now is you should watch the next video, which is me doing the section exercises of Chapter 3. After you've watched that, you might consider doing some of the other chapter exercises in the book. When you're watching me do them, you can always hit pause before I complete the solution and do it yourself. And then once you're done with that, and you feel confident that you understand what the mean, the median, and the mode is, and how they relate to our data and these distributional shapes, then you should go on and take the section exercises for Chapter 3. Let me know if you have any questions. Thanks.